You know that feeling, right? You write this piece of code, and in your head it's just so clever, so optimized, it's gotta be fast. Then you actually measure it, and it's slower than the dumb, simple version you started with. It's one of the most maddening things in programming, and today, we're gonna figure out why it happens.
So let's just dive right in. Why does this happen? Why is our intuition, our gut feeling about what makes code fast, so often completely and totally wrong? Well, it turns out the answer is buried deep down in the hardware, and all the complex stuff our high-level languages try to hide from us.
And hey, it's not just you. This quote right here says it all. This disconnect is a universal experience. It's a fundamental challenge we all face. And that's exactly why we have to stop trusting our gut and start looking at the cold, hard data.
So let's just establish the #1 rule right now, the first law of performance that you can't ever break. It's simple. Measure, don't guess. Any decision you make about performance has to be backed up by actual numbers. Data first. Always. This means you've got to get scientific about it. You start with a hypothesis, right? I bet if I change this, it'll get faster. Then you measure it to see if you were right. You analyze the results to figure out why it was faster or slower. And then you refine your code based on what you learned. It's a cycle, a process that turns guesswork into actual engineering.
All right, let's put on our detective hats. We're going to treat this like a crime scene, and our first suspect is the very heart of the computer, the CPU. Trust me, it's doing way more under the hood than you probably think. First up is this concept called pipelining. See, modern CPUs are like these hyper-efficient factory assembly lines. Instead of taking one instruction and running it from start to finish, they break it into little pieces. They can be fetching one instruction, decoding another, and executing a third, all at the exact same time. It's how they get so much done so quickly. But this beautiful, efficient assembly line hits a massive speed bump when it runs into your conditional logic. You know, all those if-else statements and loops. When the CPU gets to a branch, the whole assembly line has to kind of stop and ask, okay, which way do we go now? Now, to keep things moving, the CPU doesn't just wait around. It makes an incredibly sophisticated guess. It's called branch prediction, and it just starts running the code down the path it thinks you're going to take. But that leads to a huge question. What happens when that guess is wrong?
This happens. A pipeline flush. It's a disaster. If the CPU guessed wrong, it has to throw out all the work it just did. It completely wipes the assembly line clean and has to start all over again from the correct spot. It's a massive time penalty, a huge stall that can absolutely kill your performance if your code has a lot of unpredictable branches.
But you know, as painful as a CPU stall is, it's often not even the main villain in our story. So let's move on to suspect number 2, which, frankly, is usually the real performance killer, the memory subsystem. The problem isn't how fast your CPU can think, it's how fast you can feed it data to think about. This really sums up the reality of modern computers. Your CPU is an absolute beast, but a lot of the time it's just sitting there twiddling its thumbs waiting for data. The actual math? That's cheap. The super expensive part is that long, slow journey to go fetch data from main memory. And just how expensive are we talking? Well, getting data from the CPU's super-fast L1 cache is basically instant. But going all the way out to main memory to get that same piece of data, that can be more than 100 times slower. That gap, that massive difference, is everything in performance tuning.
And this all leads to one of the most bizarre, counterintuitive facts in all of programming. Sometimes, doing more work, like copying a ton of data around, can actually make your program way, way faster. It sounds completely insane, I know, but it all comes down to how you access memory. So check this out. Imagine you have a bunch of data records scattered all over the place in memory. To process them, you're jumping around randomly, which is super slow. The faster way, you pay a one-time cost to copy all that scattered data into one perfect continuous block. Now you can just blast through that block sequentially at full speed. That speed boost often makes the initial cost of the copy look like nothing.
All right, on to our final suspect, or I guess a whole group of them. Let's call them the concurrency gang. The moment you start using multiple threads to try and speed things up, you open a whole new can of worms, a whole new set of really subtle and nasty performance problems.
So, the classic way to manage shared data is with a lock, or a mutex. But locks have all these hidden costs. There's the overhead of just using them, there's contention when a bunch of threads are all waiting for the same lock, and then you have the risk of total nightmares like deadlock or priority inversion, which can just grind your entire system to a halt.
That's why, for really simple stuff, like just incrementing a shared counter, using a big, heavy lock is total overkill. Instead, we can use what are called atomic instructions. These are special commands built right into the hardware that are guaranteed to happen all in one go. They are so much faster, and they let you avoid all the drama that comes with locks.
And then there's this monster, false sharing. This is one of the sneakiest performance bugs out there. Your code can look totally fine. 2 threads working on completely separate pieces of data. But if those 2 variables just happen to live on the same little chunk of memory called a cache line, the cores end up fighting over it, constantly invalidating each other's data. It creates a huge bottleneck out of literally nothing.
Okay, so we've investigated the crime scenes, we've lined up our suspects. What's the verdict? Well, the real key here isn't just about fixing slow code after you've written it. It's about designing your code from the very start to prevent these performance crimes from ever happening in the first place.
Here is a perfect example of our intuition leading us astray. Typing std move when you return something just feels efficient. But what you might not know is that it can actually stop the compiler from doing an even smarter trick called return value optimization, which can get rid of the copy or move altogether. The simpler looking code is actually the faster code because it lets the compiler do its job.
And this gets to a bigger idea, avoiding what's called unnecessary pessimization. That's a fancy way of saying don't make design choices early on that paint you into a performance corner later. Don't pick a data structure that forces you to jump all over memory if you know you'll need to read things sequentially.
And this is really the fundamental tension, isn't it? Classic software engineering teaches us to hide details behind nice, clean abstractions. But pure performance often demands the exact opposite. It wants us to expose the ugly details, like how our data is laid out in memory, so we can write the absolute fastest code possible.
So, what's the ultimate takeaway from all of this? Performance isn't just some magic trick you sprinkle on at the end. It comes from a deep understanding of the whole system, your code, the compiler that's transforming it, and the actual physical hardware that runs it. Having that complete picture is what lets you build truly fast software from day one.
So I'll leave you with this question to chew on. If great design is all about navigating these contradictions, the battle between clean code and fast code, between what feels right and what the numbers prove, what fascinating new puzzles are you going to uncover the next time you sit down to build something?